Hello, my name is Holly Briggs, and this is my week 4 interview assignment. This week, the first question is explain how you'd use a linked list internally to implement a stack. Make sure you would explain the way you'd use linked list and the time complexity associated with each of the following operations. Well, a linked list um, contains the data structure that contains data, right? Each node contains data, and each node possesses pointers that point either forward or backward. In the case of a head, it only um, would point to the next, and in the case of a tail, it only point to the previous. So there are ending points, and then the nodes in between. And in the case of a stack, which is like a stack is LIFO, uh, last in, first out, meaning that as we put data or items into the stack, and in this case, in a linked list, you only add it to the end and stuff, or like pancakes to the top, and you only take from the end. So, anyway, in this case, I'll explain it using like the head is the first item in, and any nodes in between sequentially, and then the tail is the last. And then let's see when we're talking about this, but understanding that when we're adding to that linked list, we are only adding to behind the previous ones, and we're only taking off from the only accessible point really is like the end, right? That's where we're naturally taking off. So the operations would be push, the first one. Push would be to add to that stack. So we would add the next node. And so we would determine where the tail is. And we would declare the tail the previous, have it's the new items previous, have that pointer, and then declare the new item as the tail. And the time complexity for that would be big O of 1 because you don't have to iterate through anything. It's literally accessible. Pop would be to take that same item, so at the tail, because it was the last thing added, and you would remove it. You would and store it, or store it and remove it. Anyway, and then you would declare the last item. Oh, sorry, the previous item of the tail as tail. So you change the pointer, redefine that, and the operation for doing that would be the time complexity would also be big O of 1 stuff because again it's immediately accessible. You don't need to iterate or anything to get to it. And get top would be very similar to pop, except the difference is that you're returning the value but you're not removing the value. So you're checking, right? You're looking or getting a sneak peek at what is on the end of that or the top of that stack, right? Anyway, and also similarly big O of 1, um, because it's immediately accessible. And then get empty. Oh, the last one is empty. Doing that last is empty would also be very simple. Obviously, you could look at the tail, and if the tail is empty, then there's nothing in the stack. Or if the head is empty, there's nothing in the stack. Either way, those operations are big O of 1. Because yeah, if that's empty, there's nothing in the stack. Okay, we're going to move on to the next one. So explain how you would use a linked list internally to implement a queue. A queue is a different structure. Similarly, it can be used in a linked list. Same way that linked lists, have all these nodes, and they're, and because of the pointers, there's an order. A queue would be FIFO. So first in, first out. So you have the head and you have the tail, and obviously you would add to there'd be the node for the head, the first one, and then the head would have a next, there'd be a node, and then a next, there'd be a node, and each node has a previous, and unless it's a singly linked list. Similarly, you just have to do things differently. But to simplify this, we'll think of it as a doubly linked. Anyway, and yeah, you would just be adding as you add items, you would only add items to the end and stuff. And so maintain a memory of the order that they were put into the queue stuff. All right. And the operations we'd be doing with that is enqueue, which would be to add an item to the queue. That's adding to the end. And because the end is immediately accessible, we don't have to iterate through anything in order to place it there. And in order to do that, look at the tail, declare, the new node, the previous tails, the new nodes next as the tail, and then you would declare the new node as the tail. So redefine where the tail is, and that would be enqueue. To dequeue, you'd be looking at the head of this list of nodes. And at the head, let's see, to dequeue, you would declare the node that is heads next as the head, and you'd be returning the value of the previous head, right? So you're basically removing the head. And because that's also immediately available, you don't have to iterate through every operation because we know where the head is. That would also be a time complexity of big O of 1. And that would be dequeue to remove the head. And the next item in that linked list becomes the new head stuff. And so it shuffles and it maintains that order like, a line that a line in the store. All right, so that was enqueue, dequeue, size. So size is the unique circumstance here in terms of time complexity. In a queue, to determine the size, you would have to iterate through each one and basically do a count of how many items are in the linked list. And so that would have a time complexity of big O of n stuff. Because that will take as long as the queue is stuff. Yes. All right. Is empty. Very, very simple to do. You could check the head or the tail actually. The logic would work the same for either, but let's say we just check for head. If you look at the item in head and the value is null, then you know that the queue is empty stuff. Because, yeah, that would be the only conclusion. Anyway, in this operation, because the head is immediately accessible and you don't have to iterate to find it, that time complexity would be big O of 1. Anyway, I believe that's all our questions this time. Anyway, thank you so much and have a good day.